my pleasure to introduce the morning keynote speaker, Pierre-Yves Oudeyer. Pierre-Yves is a research director at INRIA, leader of the Flowers team at INRIA and ENSTA Paris Tech in France. I've always wondered what Flowers stands for, and in case you've also wondered, it is short for Flowing Epigenetic Robots and Systems. Pierre-Yves started his career in theoretical computer science at École Normale Supérieure in Lyon and received his PhD in artificial intelligence from the University Paris 6. Prior to joining INRIA, he was a permanent researcher at Sony Computer Science Laboratory for 8 years, and his research has been recognized with numerous awards and spotlights, including the INRIA National Academy of Science Young Researcher Prize and multiple Best Paper Awards. His research is focused on developmental robotics, which lies at quite an interesting intersection of artificial intelligence, robotics, and computer science. In particular, Pierre-Yves has pioneered approaches to intrinsic motivation and artificial curiosity, and has showed how these algorithms can be used on real robots and can help us better understand curiosity in humans and in animals. One of the things I personally enjoyed most about his perspective is the notion that for animals and humans, there exists no external reward, only intrinsic or internal rewards, which is quite distinct from how much of reinforcement learning research has been pursued and considered today. I look forward to hearing what he has to share with us today, and without further ado, please welcome me in joining Pierre-Yves.
Good morning, everyone. Thank you for this kind introduction. It's a real pleasure for me to be with you today. I'd like to thank the organizers for giving me this opportunity to share some of the work I've been doing with my colleagues and my team over a number of years. So children are extraordinary learners, not so much because some of them become world champions at games like Go, chess, or mathematics. Actually, only very few of them become world champions at these skills. Rather, they're extraordinary because nearly all of them acquire efficiently all the everyday skills, ranging from locomotion, building Lego structure, riding bicycles, learning language. And they do so in an autonomous manner, which means basically that there is an engineer which is retuning some hyperparameters or providing a new reward function for every new task or new skill that they encounter. Also, they do so in a developmental manner, which means that they do learn those things in a progressive manner with a specific timing and ordering. For example, they first learn how to hold their head, then they first how to creep, how to crawl with their foreheads, then they learn how to go on the walls with their 2 legs, with their two arms, then they learn how to make 1 step with 1 arm on the wall, and then progressively 2 steps, and then they leave the arm on the wall. They don't learn right from the scratch to learn to walk with their 2 feet. And so there are some fundamental questions that one can ask. First, how do developmental structures form? And also, what is their potential role? And one hypothesis we've been pursuing is that potentially the role of those developmental structures is to enable all the learning of all these skills under strong limits of time, of energy, and of computation. So basically in my lab, and more generally in the domain called developmental robotics, we study those questions from several perspectives. One perspective is that we develop algorithmic models of aspects of human development to understand better human learning and development. Then we try to apply those insights to the field of AI and machine learning to see how we can make more flexible machines. And then we try to also apply those insights to develop educational technologies. I will try today to illustrate different aspects of these dimensions. So we studied several families of developmental forces that basically act as guidances or constraints over the learning in infants. So one of them is body morphology. An example is this passive dynamic worker that was made by Tad McGeer a long time ago. So here you have no CPU, no motors. You just have the interaction between a bio-inspired mechanical structure and gravity. And this is spontaneously generating some structured gate. On the right, you will see an extension of this idea where here you have a bio-inspired vertebral column, and you have elastics all over the body, and a few very, very simple and trivial PID controllers. And yet this robot is able to equilibrate in a very robust manner. And even actually, we can take him by the hand and lead him. And this is something that's completely emergent. This is something actually we discovered while demoing this robot at a public demonstration 10 years ago. And actually at some point there were children who were playing with the robot and taking the hand of the robot, like this little girl, and the robot just followed. And Olivier Lee, who was just next to me, who was the man who made the hard work, programming everything, I said to him, "Did you program that?" I didn't know. He said, "No, I did not program that." And actually, we thought about that, and it's just that just by lifting the hands, it's changing the center of gravity, and then the game of elastics all along the vertebral column is provoking a cycle which may follow the child. And so you can see that morphology can produce actually self-organized structure, and then learning to walk, learning certain interaction with physical interaction with humans can actually leverage those structures, and it makes learning much more easy. So there are other forces we study, cognitive biases, for example. So for example, in the domain of language acquisition, children learn very quickly the meaning of new words. So for example, if I tell you, and adults also, if I tell you this is a Weebidoo, probably you will make in your head the hypothesis that this is what you know is a microphone. You will not make the hypothesis that maybe Weebidoo is something of a particular color, of a particular shape, of a particular weight. And the reason for that is that we have some kind of biases in our head where when we hear a new word, the hypotheses we prefer are in terms of what we can do with those objects. So that's what's called affordances. So there are all other families of constraints, such as, for example, social guidance. And then there is intrinsic motivation, what's called in everyday language curiosity. And today I will focus on this topic. So what do I mean by intrinsically motivated exploration? So what I mean is actually what this little guy is doing. So this little guy is alone in a room, and there is clearly no teacher or no parent who has given this guy some instructions, some external task to do. And even if maybe the final fitness function of this guy is to grow old and reproduce, you might say, like, maybe the most sensible thing to do at this point in time is just to wait, be safe, and when it's going to be hungry, the parents are going to feed it. Avoid to put the finger in the plug because it's dangerous. But no, this guy doesn't do that. He goes for the fingers in the plug, he opens the plate furniture, he breaks things, and so he explores everything. And actually he explores not so randomly, because you see it, for example, manipulate some objects, not all objects. If he would send random motor commands to his body, actually his body would very rarely even touch the objects around. And he would also play with all objects equally well, and they don't play with all objects equally often. And it's very difficult, actually, to make the children not do this spontaneous exploration. Let's look at a typical example, a typical experimental paradigm that's used in developmental psychology. So I'm going to show you a video that's about an experiment about tool use, which is often used as a benchmark for sophisticated capabilities like task decomposition or planning. And so here the idea is that the experimenter puts a very salient, colorful toy in a tube, and he assumes that because it's a very salient, colorful toy, the child will want to get that toy. And everything else in the environment is on purpose made to be very dull. No color, no apparent meaning, no familiar to the child, very simple shapes. And that goes like this. So this was a typical run of the experiment, and so the end is that here, in the typical paper written in this literature, this child passes the test. But now let's look at the making of, like the full video of this guy. Sorry, let's play that again. No, that's the following. Sorry. Let's play that again. So the parents are very happy, the mother also.
Ah, look, it goes boom, boom, all the way along. Boom, 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 boom. All right. Yeah.
And the child wants to put the car back into the tube.
Change the box.
So what the hell? The goal was to get the car. So let's look at another child. So here it's a little girl. She's extremely concentrated. Looks like she's planning for some things. Okay.
Did the car fall out? Ooh.
Okay.
Yay! Whoa!
Mother happy? Experimenter happy? Okay, so in the paper, she gets the benchmark, she succeeds, but did she really succeed? So here is my favorite child. This one does not care at all about the car, about the tube, whatever. He just discovered that with a little piece of wood, he can actually draw on the apparatus, and he can make some noise. This guy is a genius. He just invented and discovered a tool that the experimenter and the parent did not even have the idea. But he fails to the test. He fails to the benchmark. So in the paper, it's a 0. But did he really fail? So here, by the way, it's an opportunity to see that using benchmarks to evaluate some aspects of intelligence can be sometimes very misleading. I let you make the extrapolation you want. So psychologists actually began to discuss and to study such curiosity-driven exploration already in the 40s and in the 50s in the last century. And basically, they hypothesized that the brain may contain circuits that push infants to be intrinsically interested in things like novelty, cognitive dissonance, surprise, optimal challenge. And for example, recently there is the theory of flow, and flow is one of those theories which says that the brain likes challenges of intermediate complexity, and this is where the name of my team is coming on, flowing epigenetic robots and systems. But most of these theories have actually discussed those concepts verbally, and they've mostly experimentally studied not so much the underlying mechanism of intrinsic motivation, but rather the effects of being in a state of intrinsic motivation on things like memory, and also the effect in the context of the classroom. So what's the effect in the classroom of getting the children intrinsically motivated? But very little work has been done to understand the underlying mechanism until 15 years ago, where a community from different disciplines in the world, from neuroscience, from developmental psychology, and from computer science modeling, began to gather and work together. And basically, we've tried to develop some kind of framework to think in a theoretical manner about those mechanisms. So basically, we've taken the perspective of the child as a sense-making organism, which is basically exploring the world to make good predictive models, and most importantly, to control the world. And so it means that on top of a very standard learning loop, where the infant, the child, but also the adult is making experiments to learn about the world, there is some kind of meta-architecture and meta-model which is constantly monitoring the quality of the model of the world and computing some measures of interestingness to choose which are going to be the next interesting experiments. And there are several kinds of experiments that children can actually do. So for example, on the left here, you have children who can mix chemicals and they want to predict what's going to be the color of the chemicals. That's what we call prediction experiments. And then on the right, you have children who imagine in their head a goal, like building a tower or building a bridge, and then they put in use all their internal world model machinery to try to guess the action to do that. And so, based on this framework, the question we ask is what kind of meta-architecture is needed to enable children to make the kind of discoveries they make, especially when they are very little, like they discover their body, they discover basic affordances with objects, and their body lives in a very high-dimensional world. And so that's why we've been using as a tool for modeling these mechanisms robotic playground, a bit of this type, of the type that you see right now. And on the left, for example, you see a robot that's going to learn basic affordances, pushing pushable objects, grasping graspable objects. And actually, within the same process, it's going to be able to discover. So he has a vocal tract, a simulated vocal tract that enables him to produce sounds. And he will discover that the sound he can produce actually produce contingent effects and reactions from the other robot, which is programmed to react contingently to the vocalization. So that's kind of modeling the ranges of speech communication. On the left, you have another setup, which I will describe in a few minutes. And what's important to understand is that there are several kinds of ingredients that are going to be very useful to make those models work in this kind of environment. So first of all, those machines, they produce actions and movements not at the very low level, like every millisecond they decide for low-level muscle actions, but rather they use what's called dynamic movement primitives with a higher-level dynamical systems with parameters, and that's model neuromuscular synergies, which are basically some kinds of neural networks, very low-level neural networks on top of the muscle machinery, which are producing already structured movements over time. Then, also, for example, if we are modeling the discovery of affordances, we are not going to start from a perception of the world that's based on pixels. Rather, like infants in the real world, we assume there has already been long perceptual learning going on, and these robots basically perceive the environment in an objective-based manner. Another dimension and ingredient is that these robots are going to learn in a self-supervised manner forward and inverse models of the world using a lot episodic memory. And finally, and this is what I'm going to focus on today, they are going to use mechanisms for organizing autonomously their learning curriculum. So the question is, what's an interesting learning experiment? There are many ideas that have been proposed by many fields, most of the time independently. Some of those ideas are, for example, maybe what's interesting is situation or experiments that lead to high prediction errors or high uncertainty. But actually, if you put that in a robot that's put in a real world, you will quickly discover that it's producing very strange behavior. For example, you will see your robot spend all its day moving its arm and staring at the window. What is it doing? It's actually trying to predict what's going to be the next color or the next shape of the people, of the cars, or of the clouds going through the window. It leads every time to prediction error and uncertainty. You told him to maximize prediction error and uncertainty. It is doing that. So it's a bit stupid, of course. So we need to have some other kinds of mechanisms. So among the other mechanisms, one that we've been studying a lot is what we've been calling the learning progress hypothesis. And it's been particularly interesting because on the one hand, as I will show later on, it enables quite efficient learning in high dimension in robots, but it's also enabled us to reproduce and to model particular developmental phenomena in infants. And the basic idea of the learning progress hypothesis is that the interestingness of an experiment is basically proportional to the amount of change of errors in prediction or to the amount of change in goal achievement errors. And so it can be really an improvement, but it can also be a regress. So it's why we take basically the absolute value of the derivative of the errors. And why it's also important to take the absolute value is that sometimes in some environments, the learner may forget, or some aspect of the environment may change, or the body also may change. For example, the infant is growing, the body is changing, and at some point there are skills which were mastered before, which are not anymore mastered. And so the brain needs to refocus and to repractice those activities. And this can actually organize exploration. Let's see how. Let's imagine that there are 4 activities with different learning profiles. And if we basically use the principle I just presented to you, the robot is going basically to explore first the activity which has highest learning progress, here number 3. And then when it reaches a plateau, it will automatically shift progressively to activity number 2, which then has highest learning progress, while all the way along trying to avoid the activities which are either too easy or too difficult. Okay, now what I just explained to you is a bit simplified, because here you see already that there are kind of 4 activities in the world, and you already see the shape of those learning curves. But for an autonomous learning agent, it's not possible. It doesn't know that in advance. So the real difficult question is how to do that in practice in autonomous organism. So let's see a framework which enables to do that. So imagine you have some robots. They are able to produce parameterized action policies starting from state S. Those policies may be neural nets, but actually what follows, as I said, it will be dynamic motion primitives. Then they roll out for a certain amount of time the policy. Then they observe a sequence of microstates and microactions. But what's most important is that from this trajectory, they can compute behavioral descriptors, which are characterizing the full trajectory. So this could be, for example, the mean speed of an object, or the vector of parameters of a Bézier curve that's fitting a trajectory. Or that could be a learned, like a learned recurrent neural network embedding. And from this, they are going to learn 2 kinds of models. So first of all, they are going to learn forward models, which basically map policy parameters and states to the corresponding behavioral descriptors. They are going also to learn inverse models. Inverse models take as input a target behavioral descriptor, and then they provide as output parameters of policy. So for the forward model, you can use neural nets, but typically what we use is rather a combination of episodic memory and local regression, like locally weighted regression. And then for the inverse model, we typically rely on the forward model, running an optimization and initializing it, again, thanks to the episodic memory. And how do we do exploration based on that? How do we use the notion of learning progress? There are actually several ways to do that. The first way to do that is based on the forward model. Maybe you can measure the learning progress in different subparts of the forward model and sample action parameters in parts with high learning prediction progress. That's prediction experiments. And then you can also do that from the inverse model. You can measure the competence progress in different areas of the inverse model and then sample goals, sample target behavioral descriptors that maximize this competence progress. And that's what we've been calling intrinsically motivated goal exploration. And as these things may be high-dimensional and quite complicated, how do we do that? So let's take the example of prediction experiments. So this little space is the space of action parameters and of the states. And progressively, there is an algorithm for splitting that space into subregions. And in each of those subregions, the agent is monitoring the evolution of errors. And it's computing, estimating the derivative and the absolute value. And it's going to use that as the utility function of a Bandit algorithm. Here it will be a kind of X3 algorithm because it's an unstationary problem. And it's actually also going to monitor the learning progress at different levels of the hierarchy. And what's very important also to understand is that how this splitting of the space, how this categorization of the space into different kinds of experiments is made, is by using an algorithm that is trying to differentiate the different parts of the space in terms of their learning progress. That's an interesting way also to learn interesting categorization of the space by differentiating basically their learnability. And you can basically use exactly the same idea to do goal exploration. So here, those spaces are not anymore the parameters of actions, but rather the space of parameters of goals. And so basically here, that's the same idea. You're going to sample goals in subparts of the space with high expected competence progress. And there might be actually several of those spaces, and in that case, we speak about modular exploration. Okay, so let's look at how it can look like in some particular experiments. So here we see a system, a quadruped robot, which learns autonomously the mapping between its leg movements and the movement of its gravity center. So the policies are here 24-dimensional oscillators, and the space of behavioral descriptors are the translation and rotation over 3 seconds. And in the case we do goal exploration, as we don't want to engineer too much the goal space is actually much larger than what's achievable by the robot. So it needs to actually discover what's learnable and what's not learnable in the goal space. And basically, to evaluate such a system, what we can do is look at the diversity of outcomes that are found by such algorithms. So on top here, we see the diversity of behavior that are found by random policy exploration. Just below, we see the diversity of systems that are found by using the learning progress idea on the forward model. You see that it's not much different from random exploration. Then we see the result of doing random goal exploration. That's a bit better, but not so much better. But what's much better is using the learning progress idea over the goal space. And actually, we can also test the system regularly on independently generated goals. And what we see is that goal exploration using learning progress is not only faster, but also reaches better asymptotic performances. So why is this that curiosity-driven exploration of the forward model is less efficient than goal exploration? It's actually due to two phenomena, two properties of typical robotic spaces. One is redundancy, which is basically that typically there are large parts of the space of parameters who produce exactly the same outcome, the same effect. And at the same time, you have inhomogeneities, which mean that there are large parts of the behavioral descriptor space, of the effect space, which are produced by only very small part of the space of action policies. And when you explore the forward model, you basically incentivize to be good in average to predict over the space of parameters. So basically, you may learn to know many ways to produce a few effects. But when you do goal exploration, you incentivize to be good in average to produce a diversity of effects. So basically, you may learn to produce many effects, but only in a few ways. So let's see another experiment. And in that experiment, you have here a humanoid robot that can explore its body and how to interact with many objects around. Some of the objects can be learned to control, like the hand, like the joysticks, like the little ball. There are also a number of distractors around, objects that are too far away to be moved. And there are also objects that move by themselves randomly, autonomously, and can't be controlled. So here the policy space is basically a 32-dimensional dynamic motion primitive. And here the descriptor space, the space of goal, is basically modular, which means that there are several spaces describing trajectories of different objects in the world. So here goals are actually not end state of object, but full trajectory. So the robot, for example, aims to produce a particular trajectory of a given object. So let's look at a video of this system working. So initially, the system knows nothing about its environment, so it begins to sample all objects equally often. But very quickly, actually, it will discover that among the different objects, there is one which is actually producing more learning progress than the other one, and that is the hand. There are also different objects you will discover later on. Let's wait a little bit. So actually, this little ball, when it goes in certain places of the playground, is going also to produce lights and sounds. And so by initially exploring the hand, it will actually increase the diversity of movements it creates with the hand. So that's basically a visualization of the interestingness of playing with the hand. And by focusing to play with the hands among the many other objects, it will actually increase the probability to discover a movement that actually makes produce effects on the two joysticks. And the two joysticks become a source of learning progress. It focuses on them. And actually, one of them also produces effects on the electric toy, the white electric toy in front of it. And so now the electric toy becomes a source of learning progress. It focuses on that. And it's going to begin to basically play by giving goals to the toy. And then, as a side effect, you will discover quite quickly how to move the ball. And actually, you will discover a number of original ways to move the ball. We'll see that just in a short moment. So I've been a bit fast over these discoveries. He discovers a bit later on how to produce the light, how to produce the sound, by moving the ball at particular places. And then, yes, this movement. He actually also discovers one possible interesting thing, which is completely to hide the ball. And that's also something we did not expect, because it's just by chance that his effectors can do that. And all the way along, actually, he also learns not to play with other objects. So something also that's possible with this family of algorithms is that humans can come and show demonstrations, or also show saliency to particular objects to play with. What's interesting is that if you want to use that setup more from a traditional engineering perspective, and for example, you might want to use the reinforcement learning algorithms to have the robot move the ball, and of course, you don't allow yourself also to have demonstration like here at the end, then you might, for example, have a reward, which is if the ball moves 1 centimeter, that's 1 point, 10 centimeters, 10 points, 0 centimeters, 0 point. And if you do that with a reinforcement learning algorithm, a vanilla reinforcement learning algorithm, it will actually not work, because as long as the algorithm does not have any example of a policy that gives actually a non-zero reward, it will just do random exploration at the level of low-level motors, and you will wait very, very, very long before it discovers this kind of things. Instead, what's a very robust strategy to discover how to move the ball is a bit actually to forget the ball, to be curious about all the objects around, and because of the structural coupling in the environment, it will enable the robot to discover that in a few hours. Okay. In the experiments I showed so far, the goal space representation, as I explained to you, were handmade, and they were object-centered. I know many of you like to work with starting from pixels. And we've also explored this possibility, even if we think that it's not so much what children are doing, because we think that they've already acquired a high-level object-based representation when they learn affordances. Still, we tried. And for example, what we've been trying is to have an agent that is observing other agents moving around, and using, for example, a beta VAE algorithms to learn a disentangled embedding in an environment where there are controllable objects, but also objects who move by themselves and that are not controllable. And so this beta VAE embedding is then used as a space for doing goal exploration, and those different dimensions are used by the kind of algorithm I presented to you to set goals. And what's interesting is that by using the learning progress measure, the system can actually identify among the disentangled variables who may actually correspond to the different objects, which ones are controllable and which ones are not, thanks to the measure of learning progress. And so that's a way to discover discover independently controllable features. And what we could also discover in relatively simplified setups is that we can have the system work as well as the hand-defined system. In more realistic setups, like the robotic setups I showed before, it's much more difficult because those beta VIO algorithms are not robust enough, at least from our perspectives. So let's go back to children. So here I presented an experiment that showed that these kind of mechanisms are actually good candidates in principle because they enable a high efficient learning of skills in high dimensions. But what about modeling precise child developmental data? So here we have an experiment that's about modeling vocal development. And we are basically going to use the exact same kind of algorithms I presented before, but here we are going to do that into a sensory motor space that's very closely modeling one sensory motor apparatus of the human, which is the vocal tract. So we have a virtual physical model of the vocal tract, and of the organs who produce sounds, and then a model of the ear and the physiological system of auditory perception. And the goal exploration algorithm is going to explore, to make experiments using the learning progress idea to learn about that space. There is an additional mechanism here, is that in the environment, there is also a model of an existing human social peer, which has already an organized speech systems with particular vowels, for example. And basically, the learning model can also decide when and what sound from the social peer to imitate, which means to choose as a goal, based on learning progress. And what we see is that here again, we see some kind of self-organization of developmental structure. So within an initial self-exploration phase, we have a typical sequence that appears. So first, the vocal learner discovers how to control phonation. Actually, most movement of the vocal tract don't produce sound at all. Then it focuses on vocal variations of unarticulated sounds, so things like ah, rah, rah. And then finally, automatically discovers and focuses on babbling with articulated proto-syllables, which means like ba, 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 ma, ma, ma. And actually, as the vocal learner becomes more proficient at producing those complex sounds, imitating vocalization of peers starts to provide high learning progress. Initially, it makes no learning progress at all imitating the complex vocalization of the social peer, so it does not spend a lot of time imitating them. But later on, after acquiring the building blocks of vocal tract movements through self-exploration, now we can make learning progress, and now it becomes interesting. And there is this shift from self-exploration to imitation. And all those structures are typically what we observe, actually, in the development of vocalization in infants, as shown by the work of Oudeyer and his colleagues. And what's also interesting is that if we do experiments many times, we observe regularities. So there are typical stages that I just mentioned that appear very, very often, but at the same time, there are never two individuals who have exactly the same developmental trajectory. And sometimes some individuals have a trajectory that's very different. And that can be understood by the fact that actually the interaction between the learning system, the intrinsic motivation system, the body morphology is kind of a dynamical system with several attractors. And because the learning and the intrinsic motivation system are stochastics, then because of the contingency of the exploration, the system will fall in one of these different attractors. And actually, this duality between regularity and diversity is also a feature we observe in child development. And to further those experiments, we've done experiments actually to combat a bit to the kind of setup I presented at the beginning with the infants learning to use tools. And we've extended those models also to include the possibility for agents to produce sound. So here we have an agent who can learn how its body can produce effects in the environment with its arm, but also with its vocal tract. And so we have in front of this little agent a table with various objects. Some objects can be used as tools to retrieve other objects that are far away. And then there is also a model of a caretaker which is producing various kind of speech sounds. And for example, when the learning agent is touching one of the objects, then the caretaker is actually producing the name of this object. And the learning agent, again, is going to do goal exploration by setting goals, by trying to produce effects on various object environment, including the sounds. And what's interesting is that it's going to discover progressively not only that it can grasp the different objects with its hand, it can use some objects to move around the different objects, but it can also use its vocal tract to produce sounds that produce a particular effect in the other social caretaker, which is not only to produce sounds, but actually something I forgot to tell you. Also, when the learner producing the name of an object, the caretaker is basically basically grasping the object and putting it in front of the learning agent. So when the learning agent wants to play with an object, he learns that he should produce a certain pattern of sound waves, which is going to produce a pattern of behavior in the other agent, and then get the toy. So that's basically the discovery of the linguistic function of speech communication. So continuing on this track, let me now extend to a multi-agent setup, but I'm going to show you something a little bit fun because that's an art actually experiment that was made, but I thought it's fun because it illustrates some further ideas. So here basically we have not one agent, but we have several agents. They are equipped with a kind of curiosity-driven exploration system I just described to you, which enables them to discover how their movements can produce effects in the objects nearby. But they also play what's called language games. So for example, here they play language games. So one of those little robots is actually trying to have the other robot guess an object he's thinking of by producing a sound. A bit like earlier I told you Wibidoo, but I could have played the game. I say you Wibidoo, and you have to guess what's Wibidoo, and you show me with your hand. And then if it's right, I say, yeah, that's right. If it's wrong, I show you Wibidoo. And so they do that 2 by 2. And initially, they have random sounds, random vocabularies, and they don't understand at all each other. But through interaction, they progressively synchronize their vocabulary and their speech sounds, and they get to an emergent communication system. And what's interesting is that what they talk about is also their movements and the effects they discover through curiosity-driven exploration. So there is an interesting lookup of interaction between curiosity and language emergence. And now if we come back, we come back to more science, and we do these kind of experiments by actually coming back with realistic model of the vocal tract, and have these agents not only exploring the relation between their vocal movement and the sound, but they are several in an environment, and their goal exploration is also influenced by the sound produced by the other babbling agents. And so there is an incentive also to bias the goals they produce like the other agents around. Initially, they produce completely random sounds, non-synchronized. But then if we let the system run, after some time, they actually synchronize to speech systems. And again, here there is regularities and diversity. And we found that actually the distribution of vowel systems that they are producing maps very, very well to the distribution of vowel system that we find in the world languages. And this kind of models has enabled to provide new hypotheses actually in the domain of language evolution to understand how we can have a population of agents come up with a language in a decentralized manner, and also explain some of the regularities of the language structures. So now let me finish by coming back to experiment with humans. So very, very quickly, initially I began my talk by showing you experimental paradigms that maybe missed some important aspects of human behavior. And so we've been trying also to develop new kinds of behavioral paradigms to also study free exploration in humans. And the kind of paradigms we've played with and we've kind of developed is paradigms where we don't impose one task to the learners, and then we want to incentivize them to do it as well as possible, and then we study what's happening. But rather, we let subjects, here it's humans, but we are also now doing it with children, in front of many tasks, and we tell them, you're completely free to do whatever you want. You're not going to be compared to other people. And what we want to study is the structure of their exploration. So in that particular case, for example, it's video games, games like the Guitar Hero, you know, but much more simple visually. And instead of letting them begin with the easiest level, they have directly access to all levels, and they are free to explore them the way they want. And what we observe is that, interestingly, they will actually organize their exploration by quickly focusing on those levels of intermediate complexity, which corresponds to the highest learning progress that they are being made. Also, they are doing a few stuff which are a bit beyond the models, the prediction of our models. For example, what they do is that even if they know that there are some levels that are very, very difficult for them, for example, they fail completely at level 50, and still they want to go at level 70. They are curious about how bad they can be. This is not completely well accounted by our models so far. And let me finish the few minutes quickly by showing how such fundamental research in cognitive modeling and AI can also find applications in a high-stakes societal issue, which is education. So instead of generating a learning curriculum for robots or machine learning algorithms, we're actually able to show that those curiosity-driven algorithms I presented can allow to generalize personalized curriculums for human learners that maximize learning efficiency, but also motivation. So an example is, for example, the personalization of sequences of exercises for learning arithmetic skills that we've been experimenting in primary schools in France over more than 1,000 children. And so the basic idea is to track for each student the learning progress according to various properties of exercises, and then to incrementally propose exercises that maximize learning progress. So the principle is the same as before. So there is a space of exercise families organized in a graph. So here there is a graph which is constraining a little bit. And each node is a family of exercises with similar parameters from which one can sample. And so initially the system is hot started by considering only the easy nodes in the graph. And basically we use this learning progress to sample the exercise in the different kinds of exercises in those nodes. And also, we don't totally impose the exercises. We recommend exercises to the children, for example, 2 exercises, and they have the final choice. And that's also important. And then, as learning proceeds, the set of nodes in the Bandit is evolving in direction of high learning progress, and so on. And then, we study several kinds of things. First of all, we study the learning impact. So, for example, to what levels of exercises we can bring different kinds of students. So here I'm going to show a very synthesized result because we have many detailed results, but just the main idea is that if we compare the systems to what we call an oracle algorithms, which is an algorithm that was built by the hand by a pedagogical expert that is an expert in the didactics of mathematics and who tries to make a tree of exercises by trying to understand as much as he can the particularities of children by proposing certain exercises if he sees that some children are making errors. So that's what we call an oracle algorithm. We can see that actually different variations of the algorithm I presented to you not only do as well, but even do a little bit better than the oracle algorithm. And one of the reasons is that even if the human can be an expert in the didactics, he can never predict in advance completely all the peculiarities of each particular student. And we are also actually studying the motivational impact of those systems on the children. So we use relatively standardized questionnaires that are used in the psychology literature for measuring intrinsic motivation. And so, for example, what we can see is that there are some variations, some instantiation of those algorithms that enable the children also to be more intrinsically motivated about the activity of learning those mathematics than by using the oracle algorithm. So, just summary, very simple takeaway. I hope my talk has enabled you to understand the fundamental role of spontaneous exploration and development. This is, I think, a subject that is not yet completely understood and studied a lot in the domain of machine learning. I think it's a very important path for the future. I highlighted the concept of autonomous goal exploration and the concept of learning progress. I showed to you that it can be used to enable real-world robots to learn relatively complex skills in high dimensions. It can be used to model the way developmental trajectories self-organize in human infants and to model discoveries such as tool use and aspects of language. And I showed you that it can be used to gain also educational technologies. Thank you.
We have time for 1 or 2 questions, so if you have a question, please come up to one of the 2 microphones. And also, yeah, you can start setting up for the next talk. Over here.
Hello. Well, thank you for the interesting talk. I had a question regarding experiments where you have several of those robots exploring the world. Do they somehow understand or model the fact that part of the world around them is actually other agents, other robots like them?
That's a very good question. Actually, they don't. And to us, it's quite interesting because it shows that basic aspects of speech communications can be learned without having a model of the other. And that's important because there is some kind of chicken and egg problem when we want to understand the origins of communication. There are many psychologists who believe that those models are very fundamental very early on. And what we show, or we suggest, is that it is possible actually to bootstrap basic communication skills without those models. And also this enables to understand how the structure of interaction that comes out of the system can actually probably enable an easier way to build models of the other later on, because now there is this organized structure going on.
Hi, thanks for the talk. So I was curious about this part where you're talking about learning an inverse model versus a forward model and sort of arguing that the inverse model was a better target for this intrinsic motivation thing. So to be able to do that, I guess you need to have like an idea of what the states are so that you can say this goal state and this goal state are the same, even though the trajectories that got me there are different. But like in general, we'd like to deal with partial observability where we don't necessarily know the state space. Do you have a thought about like how you could do this without knowing the states in advance?
So there are actually two questions in your question. There is the question of knowing a representation of the states and knowing a measure of similarity in that space. And indeed, in the robotic experiments I presented, the one with the real physical robots, the engineer is providing tools to compute those distances. Still, there are many, many complicated problems to resolve. But then to come back to your question, there are several things we've been trying. So one of the things is when we use this VIE thing, actually the goal space is learned. And actually we use the learned space in a modular fashion. And that's a way to address that. But in other work that I don't present actually here and that we are working on right now, we are also learning this distance function by using the fact that the agent is embodied in the real physical world. And when it's moving around, you have a time structure which is correlated to the physical structure. And so, for example, you know that scenes that are perceived very close in time have a high probability to be similar, and those that are far away in time have a high probability to be dissimilar. And we use that as a training signal to train a metric learning system. But I've not talked about that at all today.
Thanks.
Okay, we're unfortunately out of time for more questions. You can take them offline. Let's thank Pierre-Yves again.